Hello, in this video we're going to go over integrable functions. In the previous video we talked about upper integrals and lower integrals. Now we want to define what it means for a function to be integrable and then find a criterion called the Archimedes-Riemann Theorem that guarantees a function is integrable, and then we will do a few examples on that. So this is going to be really helpful. This theorem is going to be very helpful in figuring out if a function is integrable or not. This would be our main tool in showing that a function is integrable. So first, the definition. We say a bounded function from AB to R is integrable if the upper integral is the same as the lower integral. And we talked about why that would have to be the case. The upper estimate that we find for the area underneath the graph of the function would have to be the same as the lower estimate. So when you look at these lower estimates, this would have to be get closer and closer to the upper estimate. In that case, we say the function is integrable, and the common value of the upper integral and lower integral is denoted by integral from a to b of f. Okay, so the main theorem for today is the Archimedes-Riemann theorem. So first, what's this statement? And then we are going to go over the proof of that, and then we will see some of the applications. Okay, so the statement of the theorem. Intuitively, it tells us that if you look at the look at the example on the right, look at these lower sums that I found. If the lower sums and upper sums are close to each other, then the function would be integrable, and vice versa. And the integral is the limit of the upper sums or limit of the lower sums. So that's what it tells us. Now, what's the regress statement? Let f from AB to R be a bounded function. Then f is integrable on AB if and only if there's a sequence Pn of partitions of AB for which upper sum minus lower sum of this function with respect to this sequence of partitions is 0. So upper sum minus lower sum approaches 0. And if that is the case, if the upper estimate and lower estimate get closer and closer to each other, then both of these two lower and upper estimates approach integral of f. Okay, so let's see how we can in fact prove this one. So let's just start with the first statement. So the first statement tells us it's an if and only if statement. If f is integrable, then there's a sequence of partitions. So suppose f is integrable. Suppose f from AB to R is integrable. So what does it mean for it to be integrable? By definition, upper integral and lower integral are the same. Now, in order for that to make sense, all of the upper sums are getting closer and closer to upper integral. Lower sums are getting closer and closer to. So if I want to look at kind of the idea of the proof, if you look at the lower integral, it is always less than or equal to the upper integral. But of course, in this case, they are the same. Upper sums are above that. Lower sums are below that. Upper sums approach this because upper integrals are infimum. Upper integral is infimum. And lower sums approach this because lower integral is the supremum of all the lower integrals, lower sums. Now, since these two in this case are the same, these two must also be close to each other, which is how we can find a sequence that approaches 0. So let's do that. For every positive integer n, this common value, the integral from lower integral minus 1 over n, is not a is not an upper bound for where P ranges over all partitions of AB. This is not an upper bound because lower integral is in fact a supremum, so that is not an upper bound. Thus, there is a partition, let me call that Qn, of AB such that the lower integral minus 1 over n is less than the lower sum of f Qn. Now, similarly, there is a partition Rn of AB such that if I look at the upper integral plus 1 over n would be greater than some upper sum. Now, I'm going to combine the two sequences of partitions and refine them. So let Pn be a refinement of both Qn and Rn. So for example, the union. Then if I look at the lower sum of Pn, this would be when I refine the partition, lower sum becomes larger. This would be greater than or equal to lower sum of Qn, which is greater than lower integral of f minus 1 over n. Now, similarly, if I look at the upper sum of Pn, since I refined it, this would be less than or equal to the upper sum of f Rn. And that is less than upper integral of f plus 1 over n. But notice that upper and lower are the same. So if you look at these two are the same. So if I look at the upper sum for Pn minus, I would like to show this is in fact approaching 0. Okay, so this is less than, first of all, this is positive or at least non-negative. Upper sum is less than integral from a to b of f plus 1 over n. The other one is also less than integral from a to b of f minus 1 over n. And this is 2 over n. Now, since limit of 2 over n is 0 as n approaches infinity, by the comparison lemma, limit of upper sum minus lower sum is in fact 0 as n approaches infinity. Okay, so this proves one direction of the theorem. So we found a sequence of partitions that upper sum minus lower sum approaches 0. Okay, so now suppose there is such a sequence. So now suppose limit of upper sum minus lower sum is in fact 0 for some sequence of partitions. I would like to show that f is integrable, which means the upper integral is the same as lower integral. But if you look at the upper integral, and look at the lower integral, upper integral is always less than or equal to the upper sums, because upper integral is the infimum of all of the upper sums, and lower integrals are greater than or equal to all the lower sums. And because of the negative sign, I have this inequality. And of course, we proved that upper sum is always greater, upper integral is always greater than or equal to lower integral. So now, if you take the limit of this, that would have to be greater than or equal to this quantity. So that means 0 is less than or equal to integral from a to b of upper integral of f minus lower integral of f less than or equal to the limit of upper sum minus lower sum. But the limit of upper minus lower by assumption is 0. This is a constant. This is a fixed number that does not depend on n, and therefore it would have to be 0. So the upper integral minus lower integral would have to be 0, which means f is integrable. Okay, so this proves the Archimedes-Riemann theorem, the first part of it, the part that tells us the function is integrable if and only if the difference of the upper minus lower sum approaches 0. Now, suppose you have a sequence of partitions that upper minus lower approaches 0. We would need to prove that, in fact, the integral is the same as the limit of each one of those. So if you look at, so I would need to prove the upper sum approaches the integral. So if you look at this, this is the same as the upper sum. First of all, this is greater than or equal to 0 because the upper integral is the same as the integral. So I'm going to start with that. So let me actually write down what I'm assuming now. So now assume, well, I guess it is part of the same. Okay, let me just rewrite it to make it more clear. Assume that the limit of upper minus lower is 0. Okay, so if you look at the upper sum minus upper integral, this is always greater than or equal to 0 because upper sum is always greater than or equal to upper integral. Now, this is the same as upper integral, upper sum minus lower integral. Lower integral is always greater than or equal to, so each lower integral is the supremum of the lower sums. So this would be less than or equal to upper minus lower. However, this guy approaches 0. So by comparison lemma, limit of upper as n approaches infinity is in fact equal to the integral from a to b of f. This guy approaches this quantity because this one approaches 0 by comparison lemma. And we could do something similar for the other one. If you take the integral from a to b, I guess in this case take the lower integral minus the lower sum. Lower integral is the same as upper integral. So this becomes the upper integral of f minus the lower sum. But upper integrals are always less than or equal to the upper sums. And then for the same reason, comparison lemma, limit of lower sum is in fact the integral from a to b of f. Okay, so this allows us to check whether a function is integrable or not. So all we need to provide is a sequence of partitions that the upper minus lower approaches 0. So that's what it means for a function to be integrable. And if we can provide that sequence, we can also potentially find the integral. We need to take the limit of those upper sums or the limit of those lower sums. Because of the significance of this sequence, we in fact have a name for that sequence. The sequence of partitions satisfying upper minus lower approaching 0 is called Archimedean. So the sequence Pn that satisfies limit as n approaches infinity of upper sum of f with respect to Pn minus the lower sum of f with respect to Pn is 0. That's called Archimedean sequence of partitions. Okay. And then one particular sequence of partitions is also pretty useful to deal with. It's basically the most natural sequence of partitions, which is called regular partition of AB. You just take the interval from A to B and divide it into equal intervals. So this one is P4. You have 5 points starting from A plus B minus A over 4, A plus B minus A over 2, A plus 3B minus A over 4, and B. So this is called P4. Okay, let's look at an example. Prove that f of x equals x is integrable. Okay, so in order to find the integral and in order to show it is integrable, we need to find a sequence of partitions that is in fact Archimedean. So we're going to start with the most natural sequence of partitions, which is the regular sequence of partitions, regular partition. So let Pn be the nth regular partition. We are going to find, look at first Pn. So Pn is divide 0, 1 into n different subintervals. So the length of each one of them is 1 over n. So 0, 1 over n, 2 over n, all the way to 1. If you look at the interval from I minus 1 over n to I over n, mi is the supremum of f of x, where x belongs to I minus 1 over n and I over n. But f of x is just x, so it is all the x's, where x is in I minus 1 over n to I over n. And of course, the largest value in that interval is I over n. In fact, it has a maximum. Not only it has a supremum, it also has a maximum. And if you look at lowercase mi, that's the infimum of x, such that x is in the interval I minus 1 over n to I over n, and that is I minus 1 over n. If you look at the upper sum minus the lower sum, you would get the sum capital Mi, which is I over n, I equals 1 to n, times the width of each interval, which is 1 over n, minus the sum I minus 1 over n times 1 over n, I equals 1 to n. Now, we're going to combine these terms. We get sum I equals 1 to n. The first one is I over n, the second one is I minus 1 over n. And then there's a factor of 1 over n. So it becomes 1 over n squared and this is n times 1 over n squared, which is 1 over n. And clearly the limit of 1 over n as n approaches infinity is 0. Thus Pn is a regular is an Archimedean sequence of partitions for f of x equals x on that interval 0, 1, on the interval 0, 1 that we were given. Okay, therefore, by the Archimedes-Riemann theorem, f is integrable. And not only that, the integral from 0 to 1 of f is equal to the limit as n approaches infinity of the upper sum or the lower sum. Either way is fine. So we're going to evaluate that. So it's the sum I over n squared, I equals 1 to n, which is equal to the limit as n approaches infinity. Now, sum of I is something we have done in before. So that's n times n plus 1 over 2. And then we have to evaluate this limit. That's pretty easy to evaluate. So I'm going to factor, cancel the n and break this down into 1/2 plus 1 over 2n, which is 1 over 2. So the integral is in fact 1 over 2. So that's pretty straightforward. Okay, so again, what we need to do in order to find the integral is find an Archimedean sequence of partitions and then evaluate its upper sum or lower sum and then take the limit. Okay, next we are going to deal with a set of functions and show that all monotone functions are in fact integrable. So that's an interesting theorem. So every function that is increasing or decreasing is in fact integrable. Furthermore, the sequence of regular partitions is an Archimedean sequence of partitions for f. Okay, so in order to show it is integrable, we need to find an Archimedean sequence of partitions for the function. So let's assume that f is increasing. The proof for decreasing would be nearly identical. So suppose f from a, b to r is increasing, and let Pn equals x0, x1 all the way to xn be the regular partition of AB into n subintervals. Since f is increasing, for every x inside the interval xi minus 1 to xi, f of x is going to be between f of xi and f of xi minus 1 because it's increasing. So that tells us mi, capital Mi, is f of xi, and lowercase mi is f of xi minus 1. In fact, it has a minimum again. Not only the infimum is f of xi minus 1, but the minimum is f of xi minus 1 because it's an increasing function. So if you would like to look at the graph, you would feel more comfortable with the graph. It's an increasing function. So the minimum is here, maximum is here because it's an increasing function. Okay, so now we'll look at the upper minus lower sum. I equals 1 to n. Both of them have a factor of xi minus 1. So what we're going to get is xi minus 1. One of them has capital Mi, the other one has lowercase mi. So let's go ahead and write this down. Substitute capital Mi with f of xi and lowercase mi with f of xi minus 1. Xi minus xi minus 1 is the width of each of these subintervals. The width of the whole interval is b minus a. Since it is regular, it is b minus a. The width of each one of those pieces is b minus a over n. And if we look at that, b minus a over n can be taken out, and the rest of the sum is in fact a telescoping sum. F of xi minus f of xi minus 1. This is b minus a over n, and that's f of b minus f of a, since it is a telescoping sum. Now, f of b, f of a, b and a are all constant. So limit of b minus a over n, f of b minus f of a as n approaches infinity is equal to b minus a is a constant. I'm using the linearity of limit. F of b minus a is also constant. So that's just the limit of 1 over n. Limit of 1 over n is 0. So the whole thing is 0. And that means f is integrable by the Archimedes-Riemann theorem. What we did was we showed that the regular sequence of partitions is Archimedean. Therefore, it would be integrable. The function would be integrable. And in fact, we showed the second part kind of automatically. We showed that the sequence of regular partitions is Archimedean. It's an Archimedean sequence of partitions. Okay, so this is very good because anytime you're dealing with a monotone function, you could just use the regular partitions, sequence of regular partitions. So far we have talked about essentially one type of function that is integrable, monotone functions. We would like to get to more types of functions that are integrable because there's actually a lot of functions that are integrable. So one type of function that is also very easy, or at least not that difficult to prove that it is integrable using the methods and tools that we have built so far, is step functions. So what is a step function? So let me go over the definition. A function from AB to R is called a step function if there is a partition Z0, Z1, Z2 all the way to Zn minus 1 and Zn of AB such that this function is a constant over each of these intervals. So over the first interval it is constant, over the second interval it is constant, and over the last interval it is constant. Now at the end points it could be that it is something different. Maybe there's a point here. So what we have is we have a bunch of different values at the endpoints. Inside the intervals, in the interior of each interval, the function is constant. So it's a bunch of constant functions put together. This function, any function of this sort, is in fact integrable. So we will prove this one. Okay. Every step function f over an interval AB is integrable. Furthermore, the sequence of regular partitions of AB is an Archimedean sequence of partitions for f. So regular partitions are going to be Archimedean. Okay, so how do we prove this one? So the way we're going to handle with this is that if you look at the Archimedean sequence, if you look at the regular partition, it would be essentially always, almost always, the values would be inside the intervals. So suppose z0 equals a, z1 all the way to zn equals b is a partition of AB for which the restriction of f on zi minus 1 comma zi is constant for all I. Now, most of the times our function is constant, which is why the upper minus lower becomes 0 in most places. So let's start with let Pm equals x0, x1 all the way to xm be the mth regular partition of the interval from a to b. So we're going to look at this these regular partitions. We are going to look at the upper minus lower. So if we look at upper sum for Pm minus the lower sum for Pm, this would be equal to the sum mi minus mi times xi minus xi minus 1, I equals 1 to m. And perhaps m is not a very good choice of letters. I'm going to change that to k, just to not confuse it with the m in the infimo. So I think I fixed it all. Okay, so pk is the kth regular partition, and we looked at this. Now, xi minus xi minus 1 is b minus a over n. So we're going to take that out, or I guess b minus a over k. So this is b minus a over k. And now I will have to show that this quantity mi minus 1, capital Mi minus lowercase mi is not too large, because this one goes to 0. If this is bounded or not too large, at least if it doesn't go to infinity as fast as k, then I would be able to say this whole thing is 0. So let's look at capital Mi minus lowercase mi. If xi minus 1 comma xi is inside zj minus 1 comma zj, then capital Mi and lowercase mi would be the same. Otherwise, it may not be the same. So, how many of these intervals are there that are not inside any of these? So, in other words, mi is not equal to mi only for those, and let me actually put it in the closed interval, for those intervals xi minus 1 comma xi that contain some zj. Now, how many of these intervals are there? So each zj belongs to at most two intervals of the form xi minus 1 xi. So at most two, one on each side. So thus there are at most two times, how many of these zj's do we have? We have z0 all the way to zn. We have n plus 1. So there are at most two times n plus 1 terms mi minus mi that may not be 0. Now look at the function. The function was a step function, so it was certainly bounded. There are only finitely many values for the function. Note that since f is a step function, its image is bounded. It is in fact finite, and hence bounded. So suppose f of x is less than or equal to a for all x inside the interval ab. So what we have is that mi minus mi would be less than or equal to a plus a, 2a. So that means if I look at b minus a over k times the sum of mi minus mi, I equals 1 to k, this is less than or equal to b minus a over k. Now there are 2 times n plus 1 terms that may not be 0, and each one of them is at most 2a. So this is what we get then. All of these are fixed. Thus, by comparison lemma, limit of upper minus lower is in fact 0. So that means pk, which was the regular sequence of regular partitions, is in fact an Archimedean sequence of partitions. Note that 1 over k approaches 0. This 1 over k that I have approaches 0. The rest are all constant. So that means, and this is greater than or equal to 0. And this guy is upper minus lower. This is in fact upper, this is what we had at the beginning, minus lower. Okay. So this proves another type of functions that are also integrable. Any monotone function is integrable. Okay. Finally, we will do one more example. So we have this is specific step function. The largest integer not exceeding x. Prove that f is integrable over each interval 0, n for every natural number n, and find its integral. So first of all, this is a step function. So f of x is equal to k if x is inside k2 k plus 1. Thus f is a step function, and hence integrable. You could also notice that this is an increasing function. So you could also use the fact that it's a monotone function. And the regular sequence, or I guess the sequence of regular partitions, is Archimedean. and the sequence of regular partitions is Archimedean. Okay, so now that we know this is Archimedean, we can find its integral. So the integral from 0 to n of f would be the limit of the upper or lower, doesn't really matter. I'll just do lower, pk, let's say, as k approaches infinity. Okay, now finding these lower sums is a little bit tricky because of the fact that you could have things that are divisible by n or not divisible by n. Because if you look at the graph, your function goes from 0 to n, and let's say from 0 to 3. So from 0 to 1 it is 0. If I draw it, 0 to 1 it's 0. From 1 to 2 it is 1, and from 2 to 3 it is 2, and then there's a 3 here. So if you divide this at these points, then it's easier to evaluate the lower sum. So let's look at the sequence of partitions that are multiples of n. So since so I'm just going to do pnk is a multiples of n is a subsequence of lower sum fpk. We have that the limit of lower sum of p sub nk is in fact the integral from 0 to n as k approaches infinity. Now we will have to evaluate these lower sums of f over this pnk, and that's not very difficult. So what we do is we take the interval from 0 to n, and we divide it into pieces. So from 0 to k, it would all be the same. The minimum, the infimum would be all 0. From k to 2k, so these are, okay, so this is just 1. The first k intervals, it would all be 0. The second k intervals, the infimum would all be 1, and so on. And then you can evaluate each one of them and then add them up. So eventually what you're going to get is, for the first one you get 0, and then for the second one you get 1 times 1, and then for this third batch you get 1 as base times 2, and the last one would be the base would be 1 and height would be n minus 1. This would be the lower sum. So you have to write it down, but it's not very difficult to see. And this is just pretty easy to evaluate. This is, yeah, so this is going to be the lower sum, and then you can evaluate this one. This is just n times n minus 1 over 2. So for example, the area here for 1 from 0 to 3 would be 1 plus 2, which is 3 times 2 over 2. So that's what you're gonna get. So there's some details that need to be worked out, but that is essentially what you get. Okay, so that brings me to the end of this video. So we will continue with the discussion of integrable functions next time, and I will see you in the next video.